Okay, so I think we're up and running. Welcome everyone. So this is a webinar that I'm going to be, well, actually my part is the easy one at the beginning to introduce and motivate some of the work, but then I'm going to introduce Dr. Andreas Olympios, who recently graduated with a PhD exactly on this topic under my supervision at Imperial. And what we were really interested in, this is work that sort of goes back maybe 4 or 5 years in terms of its inception, and some of the ideas really has to do with thinking about heat pumps, which are very interesting technology. I'm sure you might have heard of this technology that's being proposed and in some cases promoted by many as a potential solution for the decarbonization of domestic heating. Not necessarily. It can be applied also to larger scale applications and higher temperatures, but we're sort of focusing more on the domestic sector in this particular presentation. And so what we started doing with Andreas was to look at the potential of considering different types of heat pump designs and what role and what effect different heat pumps and different designs might have on the wider energy system. So I've got a couple of quick slides to just kind of motivate some of this. I will start by acknowledging that a lot of this work was done within something called the IDLES program grant, which was funded by the EPSRC. It was, of course, a program grant. It means it was a very large project. It actually finishes at the end of this month. The PI of this project was Professor Tim Green. There were, of course, many colleagues involved. I didn't have space to put them all here, and also Tim was the most photogenic, so I thought he might have the nicest photo to share with all of you. But you can see that, in a project like this, I think it spanned about 6 years, £7 million. There are many moving parts, many sub-projects, many people involved, many colleagues. And I don't have time to, unfortunately, go into the details of what the entire program does, other than, of course, I think you can get the gist of it from the title of the program. But I can tell you that the work that we're going to be discussing today really falls within this little yellow circle over there on the top left-hand side, which was Project 2, which was the project that Andreas and I were involved in. And this particular project really had an aim of trying to quantify and characterize technologies that people could use in Project 1, which was in performing so-called whole energy system modeling of the UK energy system, looking at pathways for decarbonisation to 2050 and so on. So that's in terms of how the project was, I guess, fitted within the wider IDLES program. And now I just want to sort of give you a little bit of background to this. So the idea here is that we know from a technology development perspective that there are choices that we can make when we develop heat pumps. So heat pumps are like any technology, like any product that we design. We as designers, we have trade-offs that we can make. And often those trade-offs lead to or rather, I should say, those decisions that we make lead to trade-offs between cost and performance. So the simple way of saying this is that there are ways in which we can design heat pumps to become more efficient, but these ways are not independent of their cost. Unfortunately, these high-performance heat pumps lead to higher cost to the end user, right? So the actual end-use technology becomes more expensive to purchase. So we know that there's a variability in terms of our decision making in designing these heat pumps, and the question really arises, can we try to understand what effect some of these cost and performance trade-offs have to the overall system? In other words, we know, for example, that we can design very high performance heat pumps with very high COPs, but we know those are going to be expensive. I think you can see here on the right-hand side, I'm kind of preempting some of the conclusions and the main results that Andreas is going to talk about later. So as we design heat pumps with higher and higher COPs, you can see here that the bottom part of this chart, which is basically the transition cost, which is the cost of the technology, if you like, mainly, increases monotonically, right? So the actual cost of the installation of these heat pumps into homes becomes higher because the capital cost of the heat pump becomes higher. However, because they become more efficient, so higher COP means I need less electricity for the same heating, what tends to happen is that the wider system costs, right, so to generate the electricity in the first place, so the capacity of the system and the cost associated with that increased capacity decrease. And so we can expect that maybe at some point as we increase the COP, there's an optimal heat pump design for the UK energy system that basically minimizes the total cost, both to the end user and to the wider system, to the sort of grid. Okay, so I'm making a few points there, which have to do with the fact that we wanted to try to go away from the sort of classical thinking in energy systems modeling, where each individual technology is associated with a single cost and a single performance metric, to thinking of technology, in this case heat pumps, as technologies that can have a range of cost and performance metrics depending on how you design them, because otherwise you cannot really draw reliable conclusions. And of course, I think I made the last point, which is that, you know, what if we shift costs between the homeowners and sort of the wider infrastructure, is there an optimal point which is a sweet spot in terms of minimizing the cost to everybody? And just if we can just go to the next slide, and I think this is really my last slide. So this was the motivation of us, you know, trying to understand some of this, and I'm summarizing really some of the main conclusions here, and Andreas is going to go into the details later and reiterate some of these points and explain where they come from. But really, this plot on the right hand side, I guess, is the most important one, and you can see that if we look at the optimal pathway for decarbonizing the UK energy system, and by optimal we define it in our work as the one that has the lowest total system transition cost, which is the one on the right hand side, the one with this little black line here. You can see that it's associated with a heat pump design that's neither the cheapest and neither the most expensive and the highest performing one. And there seems to be a sort of an optimal heat pump design which enables a decarbonisation of the UK energy system. So you can see here the numbers, these are the bold ones that I think you should take away. So that particular design of heat pump is associated with a 20% reduction in the capacity, in the total electricity generation capacity in the system, and a 10% reduction in the total UK system transition cost relative to other heat pump designs. So I think one of the main things that comes out of our work is that it's not as simple as saying, oh, let's just design high performance heat pumps, and that's fine, because unfortunately pushing the limits of performance comes at elevated costs, and there's a point beyond which it's better to take that money and invest it elsewhere in the system. The last thing I want to say is, you know, some people might say, well, you know, what 10% reduction in the total transition cost, is that important? And I guess the answer to that question can only be made it can only be answered in a relative sense, right? So relative to other technologies that people are thinking of. And so I'm putting there a couple of technologies that I think are featuring very, very prominently and are considered very important in the UK's journey towards decarbonisation, right? So CCGTs with CCS, and batteries, and you can see that the role of those technologies, right, or the effect of those technologies to decrease, the UK system transition cost by about 7 to 10%, which is approximately the same as what we're finding here, simply, right, by making changes to the design of the heat pumps that we are encouraging manufacturers to make, and encouraging end users to install. So with that, I'm going to pass it over to Andreas, who's going to take you through the details of some of the things that I said, and then hopefully at the end, some of the things that I said, you have more evidence to believe me. Thank you very much from my side. Andreas, over to you.
Thanks very much, Christos. Hello, everybody from my side as well. I'm Andreas, and I will go a bit into the details. I think that was a great summary of what we want to present in this webinar. I'm just going to start by saying that all this work has been recently published. So if anybody wants to read more about that, it's open source. And of course, you can ask us as well, but there is the paper online. I'll start the first few slides. I plan to show what's actually the situation now in Europe and in the UK, just to give an idea. where we are and where we should be going. You can see from this figure published by the International Energy Agency quite recently that many countries worldwide are still based on gas and oil for their residential heating. The UK is actually not doing very well. You can see that it's relatively high in this chart, but it's not just the UK, it's many countries that are still based on gas boilers or oil for their heating. And in the UK, there have been many papers, many reports about the possible ways forward to decarbonize heat. The Department of Energy Security has stated that there are three main pathways. They are electric heat pumps that run on electricity, hydrogen boilers that require hydrogen, and heat networks, which are basically which involve generating the heat in a centralized location and distributing to houses through pipes. Heat pumps, they operate on electricity, and of course, to decarbonize the system, that electricity has to come from renewable sources, and that's the main challenge. In terms of hydrogen, you have to take hydrogen to the homes, and there is the potential to use parts of the natural gas infrastructure, but actually this is not that simple yet, and also green hydrogen is very expensive at the moment to produce. So most of the recent studies and reports state they make clear that green hydrogen is a more costly pathway than electrification, and therefore it seems that there is like a bit of letting hydrogen a bit behind for now and focusing on heat pumps. Heat networks could play a role in the UK in about 20%. 20% of homes, as stated by the most recent report from the department. But that's only a target, it's an indicative target. Many local constraints can reduce the potential. So in general, it seems that electric heat pumps will be the main pathway for most buildings, for the majority of buildings, but of course they could be complemented with other options. And there has been a lot of discussions about heat pump sales in different places in Europe. We can see here the heat pumps installed per 1,000 people in different places around Europe. And you can also see here that the UK is not really doing very well. It's actually the last in terms of heat pumps per population on this figure. But what's more interesting is that in this same figure, we also plot the electricity to gas price ratio in these countries, and for 3 different years. And you can see that there is some inverse relationship between the electricity to gas price ratio and the uptake of heat pumps. So the higher the cost of electricity compared to gas, the less the operational savings from using heat pumps, and therefore the less the competitiveness. There has been a decrease, there has been a significant increase in gas prices in 2022. So you see those small blue triangles being relatively lower than on the previous points, which have increased the competitiveness of electric heat pumps in 2022. And therefore, let's see if this actually had an effect on the annual sales of heat pumps in Europe. You can see there was an upward trend in sales up until 2021. And actually in 2022, there was an even bigger increase. And that could be attributed to this fact that gas prices went up due to the various conflicts that caused gas to go more expensive, and also Europe to put some effort in reducing gas dependence. But more interesting, it's the next year, and actually in 2023 there was a reduction in heat pump sales, and that's the first time after 10 years that there was a reduction in heat pump sales in Europe. And it's not just in Europe, actually globally there was a 3% reduction in additions in heat pump technology, a slowdown that is already forcing manufacturers to reduce some jobs, and it's impacting employees. Before I discuss why this happened. Very quickly, the current stock of heat pumps in the EU, you can see that we're doing okay, but it's a bit far from the target. And why are heat pump sales dropping? A few days ago, actually, like 3-4 days ago, the European Heat Pump Association published a report trying to identify the reasons, and it was stated that the three main reasons is back in 2023, and gas prices went down again. And in many countries, there is also high inflation at the moment, high economic uncertainty, so people don't really want to invest much. And there also has been a backlash against some green policies in several countries. So those are the three main reasons heat pump sales have gone down. In the UK now, where are we? The National Audit Office also very recently published a report to assess the situation in home heating, and they've shown that the cost for installing heat pumps has slightly reduced in 2 years' time, but not as much as it was hoped, and that may also be a reason for the relatively limited uptake. And the grants that were offered were not really used that much. Maybe 19,000 heat pumps were installed using the grants, but that's nowhere close the targets. And the grants have actually been increased now with this hope to get even more people buying heat pumps. The Department of Energy Security decided not to proceed with the planned hydrogen trial for now. They plan to take more decisions on this matter later in an effort to put focus on electrification. And just before I move into our own work, I want to mention this briefing paper from the Energy Futures Lab that was published almost 2 years ago. And it aligns well with the objectives that the Department of Energy Security is setting. The main recommendation from the team at Imperial was that the government should be focusing on available solutions, so heat pumps, efficiency measures, and heat networks, and to support manufacturers to shift to heat pumps. That could also happen with consumers buying more heat pumps if electricity prices go down. And yes, the plan was one of the recommendations was again here to let hydrogen use for hard to electrify sectors for now until more research is done in the area. But there is an interesting consideration here, and okay, it's nice to say we want to help manufacturers make more heat pumps, sell more heat pumps, but actually there are many types of heat pumps. There is a plethora of design options for electric heat pumps, and the performance and cost characteristics of this, as Christos mentioned before, are correlated and are inversely correlated. So a more efficient heat pump is very often more expensive than a less efficient heat pump. So what should be manufacturers prioritizing? Should they be prioritizing high performance heat pumps from an energy system perspective that could reduce the wider infrastructure costs, but it would increase the upfront expenses for users? Or should manufacturers prioritize in affordable technologies that are easier to buy for users, but at the same time that would require more investments on the infrastructure that provides the electricity for those heat pumps? And this is the question we wanted to answer in our work. In general, whole energy system models are computer tools that are used to identify different decarbonization pathways. Same happens in the case of heating. And in traditional planning, in traditional use of these models, technology modeling would happen with some single black box or gray box representations of technologies, so some single values of efficiency and cost to represent their performance and competitiveness. And the problem with this is that the effects of choosing different components are not addressed, which leads to uncertainties and also less insights for manufacturers. And I would like to point to a report published a few years ago by a team, again at Imperial College, which was looking at different heat decarbonization pathways for the UK. And the transition cost of different pathways in that report was shown to be very close for the different options. And the authors concluded that actually no pathway can be excluded, and we should really be focusing on reducing uncertainties in our models if we want to make proper decisions. So that's our vision. Our vision was to be using detailed technology level models that capture their thermodynamic behavior, their economic components, and use this to characterize technologies in energy system models so that those energy system models can then be used not just to tell us what's the best combination of technologies in the country, but also to give some advice into what are the design parameters that we should be choosing, what are the design decisions that we have to be making to have the technologies that minimize the economic that meet the economic and environmental objectives of the country. And the way we did that was to use the expertise in our lab in the Clean Energy Processes Laboratory at Imperial. The lab has large expertise in modeling different components, heat exchangers, compressors, and all of those things that are required in a heat pump. And we used some of those to characterize the whole, let's say, a very big range of possible heat pump designs. And then we used those to characterize a few different heat pump options in a whole UK energy system model, which allowed us basically to assess the impact of different designs on the whole country's electricity generation mix of technologies and also on the total cost of electrifying heat. And yes, we think it's the novelty here is actually quantifying how all these design trade-offs affect the whole energy system. This is just a graphical way to show how we interacted within this work. So you can see an energy system framework on the top and some technology, heat pump technology models on the bottom left. And those two were interacted to provide some results that are useful both from the system perspective and the design perspective. I'm not going to go in much detail into the methods used in making these technology level models, but I'll just say that in this work the focus was on low temperature domestic single stage compressor heat pumps, and we investigated combining dedicated heat exchanger models, compressor efficiency maps for different compressors and heat exchanger types, as well as various fluids, various working fluids, and suitable equipment costing techniques from literature and from collecting data from manufacturers to see how the cost and performance of different designs are affected. It's important to state that yes, these kind of models are very useful compared to just using data from available data sheets or other information from manufacturers, because you can also test designs that don't exist yet and to also extrapolate to conditions that manufacturers do not provide data for. So this is just an example of some maps we were generating for a specific compressor, in this case, both for performance and cost. And you can see that there was also a lot of data collection in this process. This is also a list of fluids that we investigated in terms of the domestic heat pump designs. Many of these are actually phased out already or not really easy to apply in domestic heat pumps, but we tried to test different fluids just to see how their techno-economic potential would look like. And now that's it in terms of what we did at the technology site. Here I'm showing some figures that show the large variety in heat pump designs. And we are focusing on just one size, just one heat pump size. So in this case, it's a 10 kilowatt electric heat pump. And in this figure, you can see for many of our designs, how the nominal COP at the nominal conditions, how the coefficient of performance of a heat pump changes as a function of the size of heat exchangers. And yes, I guess you can see that there is some trend. So the bigger your heat exchangers are, the higher their cost, but also the higher the performance of the heat pump. And it's actually significantly affected. So the performance is significantly affected by this trade-off. You can also see with different symbols that different compressors in different conditions have various. Their performance can also vary significantly. So that's it in terms of heat exchangers. And here we also look in the comparison of some working fluids. You can see that changing the working fluid in a heat pump can significantly affect its coefficient of performance, and consequently it can also affect the levelized cost of heat when you use those domestic heat pumps. We also plot here the global warming potential of these different fluids on the right. So we can see the differences between the different fluids. It's useful here to say that R410A was the most used fluid in commercially available heat pumps before, but it had a really high global warming potential. You can see there's more than 2000. And in the last 4 or 5 years, there has been an increasing use of R32, which performed a bit better actually in most heat pump designs, and also the global warming potential was lower. Even though the global warming potential was lower, it was still high. It's still high. So many manufacturers are now switching also to natural working fluids, and actually propane, which is associated with negligible global warming potential, but has some other issues like flammability. But you can see that propane does relatively well in terms of levelized cost of heat compared to other natural working fluids. We also tested ammonia in these designs, but of course, ammonia is a very high performance working fluid, very good properties, but it's also toxic and corrosive, and therefore its use in domestic heat pumps has not really been performed much until now. But in any case, for the rest of the whole energy system results, we are focusing on these 4 fluids. And you can see they have different properties in terms of health potential for global warming, flammability, and techno-economic performance. Yes, so in this figure now, we look at the whole design space of different heat pumps. We can see the nominal heat pump COP as a function of the heat pump price. And you can actually see that for many different fluids, different compressor and heat exchanger sizes, there is a large change in the specific price. And I am reminding you here that we are just focusing on a specific heat pump output. It's exactly the same heat demand that these heat pumps are designed for, but still you can get all that variability in cost and performance. Those 4 lines on the top of the graph, they show the Pareto fronts, which basically are lines that show the set of optimal designs in which improving one objective would worsen another. So they are like the best case, the best possible designs. And you can see that they also have face various variability. So the main question is, which designs should we be choosing? Because some are cheap, some are more efficient. We didn't really say here which one we should be going for. Before moving to the energy system results, I just would like to show you this analysis from the homeowner's perspective. Of course, the homeowner looks at the investment cost, but also it would be more wise if they look at the payback time and the levelized cost of heat of installing an electric heat pump. The payback time in this work was found compared to switching from another electric heating system. Main reason being that it was actually found that it's not really worth it economically to switch from a gas system. But the point here in these figures is to show that the actual optimal heat pump performance, the optimal heat pump design, lies in the range of coefficients of performance of around 3.2 to 3.6 when looking at this problem from the perspective of the homeowner. But the whole idea is, what if we look at the whole energy system perspective? And this is where we integrated all these characteristics of different designs to a whole UK model, the hedged model that combines heat, electricity, gas, and it integrates all these vectors together in a mixed problem, which simultaneously identifies the design and operation of the energy system technologies with the aim to minimize the total transition cost while satisfying the electricity and heat demand of the country, ensuring there is adequate security of supply and services, ancillary services, and also that the country meets its carbon emissions. So we've included characteristics and we arrived to this nice figure that Christos also showed in the first slides, that shows the installed electricity generation capacity in the UK in 2050 and the associated system transition cost towards decarbonising heating with the 2 y-axis. And you can see that the UK system, the optimal UK system using the hedged model shows a mix of technologies with nuclear, gas turbines, with or without carbon capture and storage. There is, of course, wind generation on and offshore, and photovoltaic systems, as well as some help from intercollectors and notably some electricity storage in the form of pumped hydro and lithium-ion batteries. The important thing to capture from this figure is that the higher the COP of the heat pumps, the lower the required electricity capacity that is installed, and actually we see that there is a decrease in the size of in the capacity of batteries. There is a decrease, also a small decrease in the renewable electricity generation, and a decrease also in flexibility services like gas turbines when we move to higher performance heat pumps. But as we move to higher performance heat pumps, the cost of heat pumps increases, and you can see that there is actually a point where the system transition cost is minimal. And that point is here found to be for heat pump designs that achieve a nominal coefficient of performance of around 3. So that's actually slightly lower than what we've seen from the homeowner's perspective. This total system cost can be actually broken down as well into the upstream system costs, which are associated to getting all that green electricity to heat pumps, and also the cost to end users, which is the heating system in their house itself. Yes, the main point here is that after a specific point, it's overall more cost optimal to keep heat pump costs relatively low, even if that means that centrally we have to invest in more batteries and photovoltaics and other flexibility systems. So by not going for the best possible performance, we also shift some portion of the actual cost from the end user to the government side, and that could also be a way to incentivize more higher uptake. In terms of the comparison between the homeowner's perspective and the energy system perspective, you can see from this figure here that the optimal heat pump COP is different when looking at the payback time or the levelized cost when actually you look at the optimal heat pump design from the system perspective. And from the system perspective, we see that the COP is actually slightly lower. And in terms of components, it's nice just to mention here that in general, high performance compressors are usually scroll, at least for the UK weather. Of course, some rotary compressors as well, but it seems that it's optimal to go for relatively high performance compressors if you look at the problem from the homeowner's perspective and the relatively large heat exchangers, while when you look at it from the energy system perspective, that optimal point shifts slightly to slightly lower performance components and smaller heat exchangers. So that's the grasp of what we did, and I would like to conclude by this consideration, which is it worth it to invest in heat pump performance, or is it worth it to invest in whole energy system flexibility? And in this work, we've shown that component choices significantly influence heat pump cost and performance, with the investment cost varying between about 500 and 1,000 pounds per kilowatt for air to water heat pumps, excluding all the installation costs. And the COP can also more than double if you switch from low to high performance. High performance systems would lead to a reduction in electricity generation capacity. They also lead to an increase in end user investment cost. So there is actually a point there is which minimizes the cost when we are all in this together from an energy system perspective. And beyond the investing in further coefficient in further performance improvements may be less cost effective, and those resources could be more wisely used, maybe more effectively allocated in centralized renewable energy generation and energy storage. I'll just conclude by saying that some of these could be potentially translated to policy measures, because it's really important to recognize that there is a inherent trade-off between different technology options, and actually maybe it makes sense that instead of just the aim being to help manufacturers produce more heat pumps, maybe it has to be to encourage them to focus on specific designs that are the best when looking at this problem holistically. And with exactly the same idea, maybe some of the incentives for consumers could be set so that they buy the heat pumps that meet specified design and cost criteria that make sense from the perspective of the whole system. So that's it. I'll just thank again Christos, but also Puya, because this was a collaborative work between the three of us, and it actually took a few years of work. Working also with models from other people in the group. So I would like to thank all the people involved, and of course the NERC and EPSRC funding that supported this, as well as the Grantham Institute through the Science and Solutions for a Changing Planet doctoral program. So that's it, and thank you very much for listening. We would be happy to take questions.
Andrea, I think there's one question. I don't know if I should just go ahead and read out what's there, but Louise posted one in the chat. I don't know if you can open your chat window there, and
yes,
one from Peter. Yeah.
Yes. So Peter says, have you investigated the total system cost for hybrid domestic heat pumps, hydrogen boiler systems? The grid can be sized for heating on most winter days, and the hydrogen boiler used for to supplement that 10% of coldest days. So thank you, Peter. I don't know, Christos, do you want to take this or? Okay.
No, please go ahead, Andrea. I'll jump in if yeah.
So thank you, Peter. Yes. So point and the point of this work is not to exclude any other options. Of course, heat pumps are the main pathway for most buildings, but complementary use of hydrogen or other technologies would be useful. We've investigated this in other works, not in this specific one, because we really wanted to show how the trade-offs in heat pumps. But it's true that a hybrid system, especially in cold parts of the country, could also be an idea for some large houses. So I hope that's answering pretty much this question. Yeah, there's also one more question from Peter. I can see Peter says, I don't get the mechanism whereby a system that has a higher COP could have both a better payback for the homeowner, but a worse payback in terms of the system cost. Yes, so exactly this is the kind of question that we were trying to answer with this work, because a homeowner looks at the problem only in terms of themselves. What should I pay? What am I getting back? That's what determining whether an investment is worth it. But if
Andrea,
you look at the
sorry
problem,
to interrupt you. Just a quick pause. Do you mind going to the slide with the homeowner? I don't think we spoke about payback, but the economic, let's say, viability of higher COP heat pump. I think while you're answering it, it might help to see the. So there's system cost.
Maybe which slide you mentioned?
Okay, so the question, I think what we need to respond to here is this: do you agree with the two statements that higher COP heat pumps have a better payback for the homeowner?
Yes, right.
Okay, so where can we show that?
Yeah, so let's quickly put this slide. Yes, so in general, from a homeowner's perspective, we see that the homeowner will only look at the operational cost and the investment cost and make an analysis of whether this is worth the investment. And it seems that there is the design that is optimal from the homeowner's perspective has a slightly higher coefficient of performance, but the end user doesn't really know how that electricity that comes to their home should be produced, how cheap is it to do it, how expensive it is to do it. So that's the whole point of looking at the problem from a bit higher perspective and actually looking at the prices of the photovoltaic systems that will be required, the battery systems that would be required to satisfy different heat pump designs. And that gives us a slightly different answer, because maybe some of those centralized system costs are lower than the cost you need to go to a higher heat pump design after a point.
Let me add something to this, Andrea,
Yeah.
because I think there's also some confusion here. I don't know how we're doing with time, but I think there's some confusion here about what higher and lower actually means. So in my opinion, Peter, looking at plots like this, I don't, so let's say the heat pump that Andreas is pointing to there in that slide, let's say 3.2, something like that, has a better payback than other designs. But you could design even higher COP heat pumps, and they have a longer payback, so they have a worse payback. So actually, this is why I was kind of prodding Andreas before. Actually, the conclusion I draw is kind of slightly conflicting with what you're saying there. That's where the conflict comes in, that designing a very, very high COP heat pump actually has worse economics for the homeowner, longer payback periods, but a better total whole system transition cost. So that's where this conflict actually arises, if that makes any sense. There are a couple of questions, Andreas, if you can have a look, Phil and Craig. Yeah, I'm just going to mute myself.
So Phil's asking, will Imperial or the Department of Energy Security be maintaining your model so that new information about costs can be used? That's a good question. We are doing our best with Christos to, get this across. We actually also recently submitted some evidence to the department based on the results from this work, and hopefully we hope to contribute a bit into this decision making on what has to be included in the next round of measures. I don't know if Christos, you want to add anything?
Yeah, it's a very good point, Phil, because as I mentioned at the beginning, this all of this work was done within the IDLES program. The IDLES program is coming to an end at the end of this project. The danger, as you correctly identify, is that this is a fast-moving area. You've seen how costs can go up and down, and I'm sure this is what motivates your question. Within 6 months, 12 months, who knows, the values that we have there might be historical values are no longer relevant. So I think it does require Andreas and myself to sit down and think about how this can be maintained properly. It would be a shame to not keep it updated. So I think it's a very good point. I think we'll take that away as a challenge for how best to get this done. I'm aware of what you're saying. It's just a question of a mechanism. And then I think there's a final question there, as far as I can see, Andreas.
Yes, Craig is asking, what's the range of price of heat pumps on the market for the 10 kilowatt device studied?
Yeah.
And are the most expensive double of the cheapest? So yeah, that's why I brought this slide back here, just to show the large design space of heat pumps that we considered in the work. And yes, actually, that's pretty right, that the specific price can vary almost double, let's say, for the investigated technologies that all correspond to exactly the same size, same application. The only thing that changes is the components that are used to achieve that heat output. So yeah, you can see the variation in price, but also in COP, because it even more than doubles when you switch when you change the components and the sizes that you use.
Andrea, I think there's a differentiation, just to be clear and answer Craig's question, there's a differentiation between the ranges and the investigated design space that you looked at in your work, which might go outside of existing designs in them of heat pumps or the products on the market, and what is available for people to buy right now, yes, which is very different. So that would be a subset of what you investigated, because not all of everything that you're showing here is now available on the market, right?
Yes.
So I think, I mean, I know that you have done this. I just don't know whether you have that in the specific presentation.
Yeah, no, not now, but
yeah. So there is a range, Craig. I off the top of my head, I don't remember now. It is a subset of this. Maybe it's not as big as a factor of 2, but it's you know, something close to it.
yeah.
Okay.
Perfect. That's good.
All right. So yeah, I guess we seem to have come to the end of the presentation. I wanted to just say goodbye from me and thank you all for coming to this presentation. I'm sure there are many things to discuss. Some of which, you know, and maybe this Q&A part at the end of the presentation is not the right format. Andrea, I don't know if you can just, while we're doing this closing part of the presentation, go very quickly to the part with our emails, just in case someone wants to jot it down. So yeah, but I'd encourage you. I'd love to talk about any of these extensions of the work. We're still very actively working on some of these questions, especially, and there are many suggestions, good ones from Peter and etc. about next steps in terms of, you know, in looking at hybrid systems, looking at more in-depth comparisons. So we have a lot of ideas of where to take this, but also we're still really distilling some of these nice conclusions from the work that Andreas did. So please write to me, please write to Andreas. We'd be very happy to discuss further. Thank you for coming to this event. It was a pleasure. I'll pass it over to Andreas. Thank you very much from me, and goodbye.
Yes, thank you also from me. That's a good enough conclusion, I think. So for any follow-up, yes, feel free to contact us. We would be excited to talk more about this. So yes, thank you very much.
Thank you, everyone.